Okay, so welcome back. Happy New Year. Your first video of the new year, so let's start it off right. We're going to combine video number 2 and number 3 together into one. So we're going to talk about square roots, which should be mostly review because you did these last year in geometry, and we're going to talk about the introduction to imaginary numbers. So let's get the square roots done first. We all know that the square root of 4 is 2, and the square root of 16 is 4. Okay, but what is the square root of 27? The square root of 27 is 5.196 because we always round to 3 decimals. Okay, from here on out we're rounding to 3 decimals because that's what the College Board wants us to round to. But what if I said I didn't want it approximately? Because remember, this is approximately because I'm a rounding. Approximately because I'm a rounding. Yeah, that made sense. So this is an approximate answer. What if I wanted an exact answer? This is where last year you learned how to simplify square roots. And there are 2 different ways to do it. I'm just going to teach you, actually I'm going to show you both first. So square root of 27, I know I can turn into the square root of 9 times the square root of 3. The square root of 9 is 3. The square root of 3 can't be simplified. So I could do it that way. But I think the better way to make sure that everything gets pulled out is to do an upside down factor tree. So 3 goes into 27 9 times. I'm going to divide again. 3 goes into 9 3. In a square root, okay, that is implied right there, that it's a 2 in there for a square root. I'm looking for groups of 2. So there's one group of 2. If I have one group of 2, 1 3 comes out. This guy doesn't have a partner, so he doesn't make a group, so he has to stay in. Let's try that again with square root of 320. Now, looking at that, I don't know what the largest perfect square inside is, which is why I don't like to teach this way. I would prefer you do an upside down factor tree. So I'm going to upside down factor 320. I'm having trouble speaking today. That's 160. I'm going to keep dividing by 2 until I can no longer divide by 2. Well, there we go. And 5 is a prime number. So you factor tree all the way down until you have a prime number and you can't divide by anything but 1. Sometimes 2 isn't going to work, so you try 3. I'm now going to look for groups of 2 numbers that are the same. These happen to be the number 2, so saying groups of 2, I'm looking for pairs, okay? There's 2, 3 pairs. So 3 2's, since that's what the pairs are, get to come out. So a 2 comes out, a 2 comes out, a 2 comes out. This 5 guy here on the bottom doesn't have a partner, he doesn't have a pair, so he has to stay inside. 2 times 2 times 2 is 8, radical 5. If I wanted to check it, what I could do is I could actually put this in my calculator, square root of 320, and square root of 320 will get me 17.889. And then I could put this in my calculator, 8 square roots of 5, and that also gets me 17.889. Simplifying a radical from this to this is no different than simplifying a fraction like this to this. Mathematically, these have the same value. This is just the simplified version. Mathematically, these have the same value. This is just the simplified value. Let's look at operations of square roots and adding, subtracting, multiplying, dividing, all of that. When I'm looking at square roots, in order to add or subtract, the square root has to be the same. Okay, so the square root of 2, the square root of 3, they are not the same. They cannot be simplified to see if they can be the same. So I can't add those, so this is not possible. But if I look down at this next problem, I have 1 radical 2 plus 1 radical 3 minus 3 radical 2's. So square root of 2 here and square root of 2 here are the same. Remember, there's a 1 in here. So this is like combining like terms. I can combine these radicals. So I have 1 radical 2 minus 3 radical 2, and that's going to give me negative 2 radical 2. And then this guy right here, square root of 3, has no one, so he just gets tagged on at the end. Now when multiplying, it's a different case. In multiplying, insides can talk and outsides can talk. So I can multiply outside numbers, the outside of this times the outside of this, and I can multiply the inside numbers, the inside of this square root to the inside of this square root. Don't forget the outside of this square root is a 1. So if I multiply the outside numbers here, I will get a negative 6. If I multiply the inside numbers, I get 10 underneath the square root. Quickly, I should think about 10 and see if it can simplify like we learned before. And these are both prime, and there are no pairs, so 10 is simplified as much as it can. Now on initial look, this next problem, these are not the same. So again, just like I did the 10, I'm going to check out real quick to see if 28 can be simplified. And indeed, there is a pair inside 28. So 28 can be simplified. There's one pair of 2, so that pair of 2's will come out. But when it comes out, it's actually coming out to that negative 5. So the square root of 7 is prime, so it can't change. This pair of 2 will actually, that 1, 2 will come out and multiply to the 5, and so I would have minus 10. The 7 is not, does not have a pair, so the 7 will stay inside. Now notice everything that's underneath the square root, they match. So I have, again, 1 square root of 7 minus 10 square roots of 7 is going to be a negative 9 square root of 7. Now let's talk about dividing. Hopefully some of you remember that this is illegal. You cannot have a square root down here in the denominator. So we have to get rid of that square root. So in order to get rid of this square root, we are going to multiply that square root by the square root of 3 by itself. Because if I multiply the square root of 3 by the square root of 3, it's going to give me the square root of 9, which is 3. I want you to notice that there's going to be a pattern. Let's see if you pick up on it. Now, I can't just randomly multiply by 1 over the square root of 3. The value of this has to be 1. So that if I multiply this fraction by 1, I don't change the value. Multiplying anything by 1 keeps it the same. So remember, anything divided by itself is 1. So I'm going to multiply by radical 3 over radical 3. And if I multiply 2 times radical 3, like it is right here, then I get 2 radical 3. And I've already multiplied the denominator, so 2 radical 3. Now, the inside of this square root and the outside of this square root cannot talk. Inside and outside cannot talk, so I cannot cancel those out. Outside and outside can talk, and you'll see that in a minute. Okay, let's move over here. Again, I want to get rid of the square root of 6, so I'm going to multiply by square root of 6 in the denominator, but that means it has to be square root of 6 in the numerator. So 3 times the square root of 6 is 3 square roots of 6. I don't know what that was. In the denominator, I'm going to multiply the square root of 6 times the square root of 6 is the square root of 36. Well, we all know the square root of 36 is 6. Do you see a pattern? If I multiply the square root of 3 times the square root of 3, I end up with plain old 3. The square root of 6 by the square root of 6, I end up with the plain old 6. I really don't need to do this step in here. A square root times itself is just the number outside the square root. Also, this outside number and this outside number can talk to each other because they're both outside. So I can simplify 3 over 6 to 1 over 2. So my final answer here is going to be 1 square root of 6 over 2. Can I simplify the square root of 6 and the 2? Can I simplify this 6 inside and this 2 outside? That answer is a big fat no. Inside the square root and outside a square root cannot talk. No. Leave this as your answer. Well, what about this? Okay. okay? This is a problem where it has a square root in the denominator, and what you're saying is, okay, so what you just told me was just multiply by the square root over itself. But remember, if I multiply the square root over itself, I'm actually multiplying to both of these numbers. So I'm going to have to distribute this square root of 3 here and the square root of 3 here. So really quickly, if I distribute the square root of 3 to the first term and the square root of 3 to the second term, well, I just told you that if you multiply a square root by itself, it's just going to come out as the plain number. Did I get rid of the square root in the denominator? No, there it is right there. So this is not going to work. We're going to multiply by something called the conjugate. A conjugate is going to be 1 and square root of 3 will stay the same, but that's going to be a plus. And if you remember when we were factoring perfect squares, x minus 3, x plus 3, these are conjugates. The x and the 3 stay the same, one negative in the middle and one positive in the middle. So notice this was a negative, so I'm just going to make it a positive. But if I do it in the denominator, I need to do it in the numerator as well. Okay, this is a little bit more difficult, so I don't want that. I want it to be black. So I'm going to distribute here, and then these are binomials, so I need to put parentheses around them. So if I multiply 2 times 1, I'm going to get 2. And if I multiply 2 times the square root of 3, I'm just going to get plus 2 times the square root of 3, because I can't talk inside and outside. In the bottom, I actually am going to, remember that word FOIL that I said I would never say, I'm going to FOIL, but I'm going to call it distribute. I don't like the word FOIL, so I'm going to multiply the 1 times the 1, and then I'm going to multiply the 1 times the radical 3. And then I'm going to move to this next term, and I'm going to multiply negative 3 times 1, and negative radical 3 times positive radical 3. So a negative times a positive is going to give me a negative, and radical 3 times radical 3 gives me 3. Let's do the shortcut. You could go to radical 9, but that would just give me 3. In the numerator now, those two are not like terms, so I just get 2 plus 2 radical 3. In the denominator, I have 1 and minus 3. What happens to these two middle terms? Positive radical 3 and negative radical 3 cancel out, thus getting rid of my radical in the bottom, and I'm just left with 1 minus 3, which is negative 2. I'm going to rewrite this as this guy and this guy. Okay, there are two terms, so I have 2 over negative 2, and I have plus 2 radical 3 over negative 2. This will become negative 1, and this will become negative radical 3, negative 1 radical 3, because 2 divided by 2 becomes 1. Now, let's clean it up a little bit to make it proper math. Negative 1 plus a minus, I don't need, that's a minus. I don't need the 1 outside multiplying, so this would be my final answer. And again, if you went back to the original and put this in your calculator using alpha y equals, and this in your calculator, they will give you the same value. Let's try one more that looks a little ugly. Again, I just care that there is a square root in the denominator. I don't care what the numerator is. I'm looking at the denominator. I'm going to rationalize the denominator by multiplying by the conjugate. The conjugate of this is the 2 and the radical 7 stay the same, but if this is positive right here, it becomes negative here. The numerator must be the same that I just wrote in the denominator, because this value has to be 1. These cannot be different because a numerator divided by the same denominator gives me 1. Just like we said before, these are now binomials. So now I'm going to have to distribute out in the numerator and the denominator. So in the numerator, when I multiply 1 times 2, I get 2. If I multiply 1 times the negative square root of 7, I get 1 times the square root of 7, but it's going to be a negative. Now if I multiply the next one, so I multiplied the first times the 2 and the first one times the negative 7. Sorry about that bell. Now I'm going to multiply the square root of 2 times 2 and the square root of 2 times square root of 7. So a positive square root of 2 times a positive 2. Remember, outside and inside can't talk, so that's just going to say 2 times the square root of 2. Now I'm going to multiply the positive square root of 2 times the negative square root of 7. Positive times the negative is a negative. Square root of 2 times square root of 7 is square root of 14, because inside and inside can communicate. Same thing on the bottom. So 2 times 2. 2 times the negative square root of 7. 2 times the positive square root of 7. And the square root of 7 times the square root of 7. A positive times a negative is a negative. A square root of 7 times the square root of 7. Whoops. Square root of 7 times the square root of 7 gives me 7 outside of square root. Now I'm going to see if I can simplify any further. In the numerator, I do not have any square roots that are the same. I'm going to quickly look at 14 over here, and I'm going to see if I can simplify it, but 14 is the product of two prime numbers, so I can't simplify that anymore. These are all different, so that stays the same. Makes my life a lot easier. So 2 minus 1 square root of 7 plus 2 square roots of 2 minus the square root of 14. Here, in the denominator, remember my negative 2 square roots of 7 and my positive 2 square roots of 7 will cancel out. 4 minus 7 gives me a negative 3 in the denominator. So look, we did what we were supposed to do. When we started off, we weren't allowed to have this in the denominator. I no longer have a radical in the denominator. I don't care about the numerator. And this would be my final answer. Before we move on to imaginaries, I'd like you to write down these 6 problems, and I'd like them worked out before class tomorrow. You will be handing these in, and we will go over them in class. So what is an imaginary number? Okay, so in Algebra 1, you learned about number sets, okay? And you learned that there's a real number set that's divided into 2 groups. One is, let's put reals outside. One is called rational numbers, and one is called irrational numbers. Irrational numbers are ugly decimals, like pi, like square root of 5, like square root of 32. They just, if you put them into your calculator, they're just ugly numbers. Rational is anything that can be made into a fraction, ratio, fraction. So 1/2 is a rational, -5 can be made into a rational by putting it over 1. Square root of 4 is rational because that's actually 2. So those are pretty numbers. 0 is a rational number. 1 is a rational number. 3 over 7 is a rational number. Well, what happens with imaginaries? Completely outside of the reals are these things called imaginaries. Imaginary numbers. Why do we need imaginary numbers? Well, there are many reasons, but for what we're doing right now, let's consider quadratics, and we talked about this today. We crossed about where a quadratic crosses the x-axis is a real solution because it hits the x-axis. Even if it only hits once, it still has a real solution. That, remember, would be called a double root. But what if I had a quadratic that looked like this? Will it ever hit the x-axis? Or like this? Would that ever hit the x-axis? Those are never going to hit the x-axis. So you would think that you would say they don't have a solution. Well, they do. They have imaginary solutions. So these two guys right here have imaginary solutions. What is an imaginary number? We just finished doing square roots, so if I put in the square root of 4, it's going to be 2. If I put in the square root of 9, it's going to be 3. If I put in the square root of 27, it's going to be that 5 point whatever number. If I put in the square root of negative 4, my calculator is going to give me an error that says no non-real answer. Well, what does that mean? If something is non-real, it is imaginary. But we have to be able to write that number somehow. So here's how imaginaries work. See that little negative in here? It just comes outside and becomes an I for imaginary. And if you look above your decimal point on your calculator, so if you look second decimal, you're going to see a little teeny I. That's our imaginary numbers. So what happens to the square root of 4? Well, the square root of 4 is still 2. So it becomes 2I. So square root of negative 9 becomes, the square root of 9 is 3, the negative becomes I. The square root of 27, negative, becomes 5 point ... I. Okay? If we were going to keep it exact, remember we did this back on the first page, it would be 3 radical 3, and then put that little I right in there. Right in between the whole number and the square root. Right in there. Okay. So real quick, this little guy comes out as an I, 16 is a 4. This little guy comes out as I, but the square root of 5 can't be simplified, so it's just going to stay the square root of 5. Notice the order that I'm putting these in. Here's my whole number, my coefficient, my coefficient. Here's my imaginary, and then after the imaginary comes the radical. Square root of 60, so I'm going to 15 can only be divided by 3 now. Okay, so again, I'm looking for a pair. So here's a pair of 2's. So 1 pair of 2's comes out. 3 times 5, they don't have pairs, so they have to stay in. No negative, so it just stays 2 radical 15. This guy, the I comes out. Now, 252, divide by 2. Keep dividing by 2. I don't think that will divide by 2, so I'm going to divide by 3. I'm going to divide by 3 again. Now I'm looking for pairs of numbers. Here's a pair. Here's a pair. So 1 pair of 2's, so a 2 gets to come out. 1 pair of 3's, so a 3 gets to come out. 7 doesn't have a pair, so he has to stay in. I multiply the 2 times 3, leave the I, square root of 7. Unfortunately, this is not, you cannot check this in your calculator because you can't put this in because I get non-real answer, error. So you can't check an I in my calculator. What I can do is put square root of 252 in, 6 square roots of 7. So avoid the I. Just see if these have the same value. I know all the I stands for is that negative. So that's how you could check it. I'm sorry the video was so long. See you in class.